Hello, welcome to the 12th USP webinar. And my name is Ming Xiao, past president of the US Permafrost Association and a faculty member of civil engineering at Penn State. Today, we have a great pleasure to have Dr. Minnie Dogan from Western Michigan University to give us a talk on the airborne and ground-based geophysical imaging fundamentals and applications in permafrost characterization. First, I'd like to spend a couple of minutes to introduce the format and our speaker. The 2025 USPA webinar series is sponsored by Arctic Foundation's P&D engineers, Shannon and Wilson and WSP. And since this is a webinar format and our attendees won't be able to speak, so if you have any question, please type under the Q&A button. And if you click the Q&A, and you can type the questions throughout Dr. Dogan's presentation. Well, first, a quick brief introduction. And Dr. Minnie Dogan is a near-surface geophysicist specializing in environmental applications of geophysics using ground-based and airborne geophysical methods. She's an assistant professor of geophysics at Western Michigan University, teaching geophysics, numerical methods, and groundwater modeling. Her research focuses on developing high-resolution data collection methodologies for mapping groundwater contamination due to landfill leachate, delineating highly heterogeneous unconsolidated sediments and permafrost soils, and forensic applications of geophysics. She has conducted a drone-based geophysical survey in Geophysical, Alaska, and her new research projects include US-borne geophysical imaging for permafrost characterization and environmental hazard detection. Well, I just want to add that you can type in your questions and you don't have to wait until the end of it. So, Dr. Dogan, and thank you so much. And you have about 45 minutes also and to present, and then we'll leave last 10 minutes on Q&A.
Okay, thank you. Thanks very much. Welcome, everyone. It's a privilege to be able to present and share my experience related to the use of geophysical methods for permafrost environments. So today I'm going to talk about the conventional methods of geophysics for the, oopsies. Can you see the next slide?
Not yet.
Oh, yes.
There
Okay.
we go.
Okay. My screen froze for a second when I said permafrost. So today I'm going to talk about the possible targets we can encounter in the permafrost environments, their geometries and scales, and also their physical properties, since as geophysicists, we look for those distinguishing properties to locate our targets. And then I'm going to talk a little about the conventional methods of geophysics for permafrost characterization and some on-ground applications from literature. And following that, I'm going to talk about the drone-based applications, especially very low-frequency electromagnetic method, and the challenges and the solutions we experienced during our field excursion last year in Utqiagvik. So first, the targets. As geophysicists, when we look at the ground or any kind of geologic material, basically, we think of them as targets. And the simplest targets we can see in an environment would be the horizontal boundaries. When it comes to the permafrost environments, this can be the boundaries between surface soil layer and sand or clay layers, and from clay layers or active layers to permafrosts. And these horizontal layers can be actually in quite small scales, especially for the shallowest part of the ground, that can be sub-meter to a few meters scale. While we expect them to be relatively easier to resolve due to their geometry, because of their thicknesses, the resolutions we will need to collect the data would be much higher than larger targets. Next, we can have vertical boundaries. So in the schematic going from left to right, you can get to the vertical boundaries underneath, obviously, the active zone, vertical boundaries of an ice wedge, or a boundary between continuous permafrost and discontinuous permafrost, or starting and ending edges of a talc. So this is like a combination. Now, this schematic is a combination of the horizontal boundaries with some vertical boundaries. And the scale for these can be meters to several tens of meters, sometimes hundreds of meters, depending on the environment we are looking at. And in addition to these horizontal and vertical boundaries, we also can encounter with 3D objects. And usually ice wedges are a good example for these 3D objects because all three dimensions of the ice wedge can be pretty close to each other. And these kind of objects are the most challenging ones for us to resolve. After talking about the scale and geometry, now I'm going to talk about the physical parameter contrasts and then the relative geophysical method we use that physical parameter. First, let's start with electrical resistivity or inversely electrical conductivity. I have four geologic material in here listed: topsoil, sand, clay, and weathered bedrock. And as you can see, their electrical resistivity ranges are quite diverse. Topsoil has a lower electrical resistivity range. It's higher compared to clay, but lower compared to sand. So this is actually what we are looking for. We are looking for the contrast differences between the targets and the surrounding materials, or between the boundaries. And on top of those four geologic materials, I also listed over here 5 different materials. They can be the materials we usually observe in permafrost environments, including air, fresh and salt water, sea ice, and deep ice. And as you see here, fresh water has an exceptionally high electrical resistivity compared to salt water, and sea ice, again, like salt water, has a lower electrical resistivity compared to a really high electrical resistivity of deep ice. So this basically tells us that in an environment, we should be able to separate, or we should be able to see the contrast between these materials due to the differences in their electrical resistivity values. And to measure electrical resistivity, we use electrical resistivity tomography. And you will see on the top right side over here of my presentation, it says active with galvanic connection. These are two important definitions for us geophysicists. When we say active, we mean we are actively creating an impulse. And then we are measuring our response through a galvanic connection. And with electrical resistivity tomography, we need to maintain that galvanic connection through either stainless steel electrodes or ceramic pots, non-polarizing electrodes. And when we do that through these electrodes, using one pair of electrodes, we inject electric current into the ground, and using a second pair to and we use a second pair to measure the electric potential, electric potential difference in the ground due to the electric currents we injected. The instrumentation is quite easy, much less expensive, and easy to use. The physical basis is very simple, Ohm's law. So basically, the potential difference you could create by giving any amount of electric current into a material is proportional to that material's resistance. Having water, clay, reducing chemicals, ionic content or salt, and metallic minerals, etc., decreases the bulk resistivity of any geologic material, which is defined by Archie's law very nicely for specifically water. And over here, it's the highlights of the method. So the targets are mostly near surface, down to 200 meters or so, because you are limited with the amount of current you can pass through the ground. It may require generators to be taken out to the field, but in the end, we are limited. Our electric current is going to be spent through the ground material while it's going down and then coming back us to our second pair of electrodes. And when we look at these top 200 meters or so of the ground, what we usually encounter or can measure with electrical resistivity tomography are clay layers, faults and fractures, groundwater, metallic minerals, archaeological remains, or permafrost features. And when we do that, the resolution of our data, spatial resolution of our data, is highly dependent on our electrode arrays. Also, different electrode array types can actually be more sensitive compared to another array in terms of the vertical or horizontal boundaries. So we need to choose from many of those different array types, and sometimes can come up with our own array type depending on our purpose and the resolution we would like to achieve. The pros or the advantages of this method: it is very easy in application, very easy in interpretation. What we are measuring is apparent electrical resistivity of the ground. We need an inversion algorithm to convert it to real electrical resistivity. But again, all these algorithms are much easier compared to many other methods of geophysics. It is cheaper than most methods. And you can use it in 1D applications for horizontal boundaries through Schlumberger array. You can use it for 2D imaging along profiles or cross sections, as you've seen up in here, using Van Aer or dipole-dipole or many other actually arrays. You can pick whatever you want. And then you can put many of these lines together parallel and create a 3D volume of the electrical resistivity features. And up to here, it is great. But when it comes to the challenges related to the method, first, we need a galvanic connection. And maintaining a good galvanic connection with the ground through our electrodes with a decent contact resistance is sometimes a challenging task, especially when you are in permafrost environments and trying to push electrodes through the frozen soil. Another challenge we have this method is its non-unique nature, non-unique behavior. So sometimes inversion algorithms can give different solutions to the same data sets depending on the thickness of the layers and their electrical resistivity multiplications. We can use permanent electrodes. We can bury our electrodes into the ground, leave them there so we can collect temporal images without the issue of relocating our measurement points. There are also moving vehicle applications for faster measurements to cover larger areas. And there are also even some marine applications where you pull your electrode string on a boat. One little thing I want to mention about the electrical resistivity tomography is that while it still measures electrical resistivity and physically electrical conductivity is the reverse of it, in terms of its sensitivity and resolving power, electrical resistivity tomography is more keen, more sensitive to distinguish the resistive features compared to the conductive one. So this is something to keep in mind, and we are gonna get back to that in a bit. This is an example from a paper from Leger et al. About open tundra in Alaska by Utkavik. Over here on the left side, you see the aerial photo of the measurement location. The blue line is the measurement location, and the magenta color actually shows the surface topography for this line. On the right side, we have a really nicely inverted electrical resistivity tomography data. It is around 28 meters or so in horizontal scale and 5 meters or so in the vertical scale. And now when we just look at it, right, we looked at the electrical resistivity of ice and it was exceptionally high. And over here, we see this really high electrical resistivity value nicely in shape of an ice wedge right underneath the trough over here of this polygon. So this actually tells us that electrical resistivity can indeed measure where the ice is. And above that, we have this thin layer, approximately half a meter thick layer of active zone, likely because the electrical resistivity of the zone is much lower relative to the ice. Now let's switch to another physical parameter. We're going to talk about P-wave velocity. While you see P-wave velocity in here, I also want to mention that S-wave velocities are similar to these, just lower than these numbers. When we look at our, again, four geologic material, their P-wave velocities change depending on the material. We have a contrast in here. Topsoil has quite low range of P-wave velocity. Sand can go up higher than that. And then other 5 materials we have listed over here. Ice, sea ice or deep ice, it doesn't matter, is going to have an exceptionally high P wave velocity compared to freshwater or seawater again. And now we are going to look at seismic method. We use the seismic wave velocities to distinguish different boundaries. So seismic method, again, is an active one. So we actively create an impulse by a hammer, by weight dropping, by something as elaborate as a vibrophase, but we create our own source. And what we measure is the seismic wave velocities of different layers. And we do that through geophones. So we require galvanic connection. We need to push this geophone into the ground. Inside the geophone, we have a coil, a magnet, and springs holding them together. And according to Maxwell's equations, we know that a moving magnet creates a changing magnetic field which induces electric current in the coil around the magnet. So that electric current is what we are measuring in our seismic instrument. In the end, we convert those arrivals of the reflected, refracted, and direct waves to our geophones to the seismic wave velocities of different geologic materials. This is great. Seismic, especially seismic refraction, has a great power to resolve especially horizontal boundaries. But the problem in here is going to be the resolution, because geophone spreads aren't usually, like they usually around a meter or more with separation. And also creating an active source in Arctic tundra is not an easy task, especially during summertime when you have the active layer. The ground acts almost like a sponge, and transmitting the source signal you created to your geophones is a cumbersome job that involves a lot of noise also being recorded. About the highlights of the method, seismic is a great high-resolution method for deep and large-scale targets. It allows us to image faults, structural discontinuities, and used for hydrocarbon exploration for especially seismic reflection. And besides all these advantages, it also provides a direct rock physics parameter. This is very important because in most of the cases with geophysics, we sometimes we have to rely on some indirect approximations to the physical parameters, but seismic isn't like that. Seismic, like gravity, gives you the actual rock parameter. While you need galvanic connection, we could actually overcome the issue in marine environment, so that can be used to map bathymetry. The challenges related to the method, again, its resolution, source transmission in a permafrost environment are really challenging, but also it's expensive. It's a large-scale operation. It requires a lot of processing, and sometimes it is hard to interpret. We can use it 1, 2, 3, even 4D applications. These are all good, but when it comes to using seismic method in a permafrost environment, we have to be a little creative. So this is a paper from Torre et al. From, again, the same tundra, Arctic tundra, Enutgavik. And here, seismic method is being used to map the seismic wave velocities under the ground. But when we are doing that, when the researchers doing that, they do it in a little novel way, in a different way. So first of all, as a source, they are not looking for P waves or S waves. Instead, they are working with surface waves. So the surface waves are their sources. And surface waves are around all the time. Actually, the ocean, the atmospheric changes, human like traffic, urban life, animals, wind, these all keep the ground in a constant vibration state. So we can use these waves as our seismic sources. And this study does that. And when it comes to the receivers, instead of using individual geophones installed into the ground, they use a fiber optic cable, which is designed specifically to inspect a laser ray going through the cable. And the cable, the path of the laser gets affected by the little changes of the cable, so it can be used as a seismic receiver. Over here on the right side, you see a profile electrical resistivity transect with the active layer on top with low electrical resistivity. And then we have this high electrical resistivity area, which is likely the ice permafrost layer. Now, this is along the same transect, but using a DAS cable with multi-channel analysis of surface waves. And as you see, we have this top layer over here with low wave velocities, seismic wave velocities, and then increasing seismic wave velocities for the frozen part. And there are several more actual transects over here. Some of them are really interesting to me, so I wanted to talk about them. Like over here, for example, we have one polygon that isn't as distinct as the other ones. And when you look at the seismic cross-section, created for this little line over here, it's like 23 meters long. We have low seismic wave velocities, active layer. We have high seismic wave velocities, permafrost. And over here, we again have lower seismic wave velocities. But there isn't a significant, like distinctly sticking out high velocity feature here. But over here, there's another polygon. This is more distinctly defined, like visually. And we see on the beginning part of it, over here, we have low seismic wave velocities. And then over here, down deep, we have a really high seismic wave velocity. So it actually tells us that there's more frozen content over here. And the third one that I find really interesting is this transect by a road. It is interesting that the high seismic wave velocities over here are such smooth, uniform manner, and they cover quite larger depth compared to the one in open tundra. But this tells us that the seismic waves actually help us to map the permafrost features. Now, the next physical parameter we are going to look at is going to be actually a pair, relative dielectric permittivity and electromagnetic wave velocity. They are derived, the wave velocity is derived from relative dielectric permittivity. And indirectly, I also want to talk about the electrical conductivity over here because it highly affects the attenuation of our signal. And the geologic materials, the electric permittivities are in a pretty limited range, but water has exceptionally high dielectric permittivity. So this basically tells us that we can see water quite neatly. And then we have ice with the dielectric permittivities of 3 to 4 range. The method I'm going to talk about is ground penetrating radar. It is an, again, active method. So we have to create our own source to be able to measure an impulse. But this time we don't need a galvanic connection. We can get away with the inductive connection. That is a great thing because that means you can drag an antenna behind you without poking anything into the ground to be able to measure your data. Over here on the right side, you see some unshielded antenna sets. The lower the frequency, longer the antenna is going to be. These two antennae are identical. Depending on the electronics you attach them, they're going to become transmitter or receiver antenna. Like seismic, ground penetrating radar also works with the optics rules. And it can give us an exceptionally high resolution information about the ground material. So our targets are much shallower and small scale, especially for mapping sedimentary structures, locating utilities or archaeological remains for forensic purposes or permafrost delineation characterization. We can use GPR quite successfully. With the permafrost, though, we are limited with the electrical conductivity of the material since it attenuates our signal, so limits our penetration depth quite significantly. The advantages of the method, it is a high resolution method. The measurements are really quick with the high-tech equipments. And as I said, we can just drag an antenna behind us. And not having to get into a galvanic contact with the ground actually allows us to use this method for airborne applications. It has its own challenges, but still there's a possibility of using it. In terms of the other challenges related to the method, the data processing is quite intensive. Reflection parameters can be a bit indirectly telling things about the rock properties, and the anomalies can be complicated to interpret. Again, we can collect data from 1D to 4D with really high resolution. We can use it in water as long as you keep your electronics dry, you're safe with it. And aerial applications are possible. But at this moment, I want to open up a little parenthesis and mention that when it comes to the aerial applications of the method. So we have two issues when it comes to using GPR on a drone platform. First, we have to be close to the ground surface because there's something called Fresnel opening. An electromagnetic signal, once it's out of your transmitter antenna, it opens up in a conical shape. And with depth, the area antenna the signal illuminates is going to increase. When it is doing that, while it's illuminating a bigger area, it also is losing its resolution. So this is one big challenge, a caveat that tells us that we can't get good information from the deeper ground. So we have to be closer to the ground surface to be able to send our signal with the minimal Fresnel opening into the ground. And the second problem is that the contrast between the dielectric conductivities of air and ground is so significant. The moment our signal hits to the ground air interface, almost half of it is going to reflect back to the air. So compared to having our antenna coupled with the ground, we are basically starting with almost half the energy to measure the features under the ground. So this limits our penetration depth quite significantly. This doesn't mean that we still can't collect data about the active layer, but these are two important things that we have to be careful about. And here, this is again from the earlier paper I mentioned from Leger et al. From Alaska, Utqiagvik, open tundra. But I really like these computer models. So I want to start with one of those on the left side. There are three models in here. Two of them have the same scale ice wedge with the same background of the electric permittivity of 5. The electric permittivity of 3 is ice. We talked about that. And one of them have a uniform top layer. It's like half a meter or so thick top layer, which is approximately same with what we measured last year in Alaska. And another one have this highly heterogeneous environment as a top layer. This is what we see actually out in tundra when it comes to active layer. And as you see in comparison between these two models, the GPR signal is much brighter where you don't have all those heterogeneities in the top layer to lose your signal to, because wherever you have a reflection, you are losing part of your energy. And over here, we still can see the geometry of the ice wedge, but due to the heterogeneities on top, now the signal intensity is less. And over here, this is another really nice example that when you have an asymmetrical geometry of an ice wedge, you still actually can resolve it using GPR. So I'm going to go back to the example I gave before, that line over this these polygons. This was the electrical resistivity data we looked at previously. And this is the GPR data collected along this same blue line. And you see with these red markers, we actually can see the permafrost table. And where we have more ice, like here, due to the contrast being bigger between ice and the active layer, we are seeing these multiples that actually tells us where the ice is gonna be. Over here and down in here from the bottom of the ice wedge, we have some multiples. Okay, and another physical parameter contrast is electrical conductivity. We have again for same for geological material and then water and ice variations. And the method we use to map the electrical conductivities is electromagnetic methods. I'm not going to talk about the time domain electromagnetic here, but because they are harder to use in a permafrost environment, but I'm going to talk about continuous wave or frequency domain electromagnetic methods. The system is very straightforward. Following Maxwell's equations, you have a transmitter coil creating a magnetic field by passing electric current through your coil. That magnetic field travels under the ground, goes through the conductive material, induces a set of secondary fields, and you measure those secondary fields through your receiver coil. The instruments can be quite different. This is a sling ram. It can be like a loop to carry around, can be a small coil encased in a box, or it can be a pole like this with transmitter and receiver coils on both ends. The nice thing about continuous wave or frequency domain electromagnetic methods, you still are having an active source created at the field, but it is an inductive connection. And again, like GPR, you can just walk around to collect your data. The highlights are targets can be shallow to moderate depths, but in contrary to electrical resistivity, now I'm going to tell you that electromagnetic methods are more sensitive to delineate the conductive materials, conductive targets. So we can locate metallic minerals, groundwater contamination, clay layers, some horizontal discontinuities using frequency domain electromagnetic methods. The advantages, it is really quick in terms of the measurement time. And if you can access a place by walking, you can simply collect your data without any issues. And it is, again, highly sensitive to conductive materials. It has challenges. The depth information is qualitative. So with these methods, we can't get a real depth information. The data we are collecting is a cumulative response of the ground from the depth of signal reach, skin depth, to the ground surface. To be able to eliminate or separate the parts of the data coming from different depths can be quite challenging. So it requires some advanced inversion algorithms. Where you have a superficial clay layer or highly conductive material, same with GPR actually, it acts like a blanket. So your signal, even before it travels into the ground, gonna be spent quite a bit. And it is challenging to separate the anomalies from noise, but this usually is acceptable in like urban settings. So in open tundra, we didn't get this kind of a problem when we try EM31 out there. So without galvanic connection, of course, we can have marine and airborne applications, and actually conventional airplanes or helicopters are being used very widely for collecting electromagnetic data. So I'm going to show you an example. Electromagnetic data collected over Alaskan permafrost. This is from Misley et al. It's an exceptional data set, I want to say. They use the conventional airplane to collect frequency domain electromagnetic data. The black line on this map showing the reconnaissance survey, and over here in this little box, they collected much higher resolution data. This is a conventional plane again, and the flight altitude was 30 meters. This is really, really good. And the speed, the ground speed of the plane was 30 meters per second. This is an important thing because this actually limits our spatial resolution quite a bit. Even if you are sampling your data like with 10 hertz sampling rate, say 10 samples per second, you still can only achieve 3-meter separation between your measurement points, but the data quality is really great. So here, these 3 black lines over here are the locations of these 3 cross sections, and the color scale on the right shows the electrical resistivity distribution. On top, we have this very thin green area that shows low electrical resistivity, so likely the active layer. Underneath that, we have a pretty thick red area with 2,000 to 3,000 ohm-meter electrical resistivity, so frozen ground. And underneath that, we have some really highly conductive material. So this tells us that continuous wave EM is a great method to map permafrost. But let's talk about the scale. This is more than 20 kilometers in horizontal scale and 150 meters in vertical scale. When you are interested in higher detailed, higher resolution, smaller scale targets, This cannot be a very useful method, obviously. What can we do? We can use drones instead of conventional airplanes because we can fly lower and we can fly slower. That can improve our resolution. But before you start working with drones, you got to be careful about the safety rules and regulations. Picking which power source you are going to use for your drone is one thing to decide. It can be battery, an electric powered drone, or a gas powered drone. I personally picked a battery powered drone because in Michigan we have a lot of wooded areas and gas powered drone would be a big fire hazard. So for safety reasons, I picked the battery power. You need to follow up with the country-based regulations. Some countries don't even allow you to fly. And you also need to follow with the airspace regulations. You need a license to be able to fly a drone, especially at this size. And you cannot fly close to the airports. You cannot fly in the urban settings, cities, without a permission acquired earlier. So these are all the things we need to follow. The second important thing about drone-based applications, we need to be careful about our payload. The probe, the geophysical instrument you would be attaching to the drone should be at a level of weight that can be actually carried by the drone, and also to be able to carry it for long enough time so you can collect the data you want in a larger, area. This is an Alta X, FreeFly Alta X. This is a drone that I own and use in my lab. This drone can carry a little more than 15 kilograms of a payload for 14 minutes. The probe we use is not 15 kilograms, but because of the way we attach it to the drone, we need this extreme payload capacity. Next thing to give a thought about is the probe design. Our measurement setup is important. Are you gonna power your probe through a separate battery, or are you gonna tap into the drone battery? If you tap into the drone battery, then you need to be careful about your flight times because you would be draining the battery through the flight and also through the probe. The probe's position, where it is in terms of its altitude and GPS location, are important, and in some cases some methods require you to know the exact geometry of your probe in 3D space. So in those cases you would need a tilt meter and maybe a gimbal platform. Sampling is another important thing to consider. Our sampling frequency is something we need to decide about while we are deciding about our flight speed. With this drone, you can fly as slow as 3 meters per second. So if I am, again, sampling for 10 hertz, 10 measurements per second, that means I am actually collecting one data point for every 30 centimeters. It's an exceptional resolution. Also, we need to consider what our altitude is going to be, because when you are further away from the target, the sensitivity of your instrument to detect that target is going to drop. So we want to be as close as possible to the ground surface. Another important thing about the probe design is the data quality. We want to maintain our data quality and protect our probe from the noise sources of the drone itself. Like radio frequency controller we use to communicate with our drone is a source for noise. The aircraft electronics, aircraft power, propellers, etc. are going to create electromagnetic fields, so there are going to be noise. Also, we need to be able to communicate with our probe. We can do that through ground radio stations or Wi-Fi. Now, the method I'm going to talk about is the very low frequency electromagnetic method. Why we use this? Because this method does not require you to create an active source in the field. Instead, it uses the military radio stations distributed all over the world. They are really, really strong stations with huge antenna arrays. This is from Cutler, Maine. There's 2 of these in Cutler, Maine. It's one of the I think it's the most powerful radio station, military radio station in the world. It is designed to be able to communicate with the submarines and long distance communication for army purposes. But over here, the radio transmitter in the end broadcasts an electromagnetic field. And if you are far enough away from that electromagnetic field, you can assume that your primary magnetic field coming through the electromagnetic field propagation actually can act like a horizontal wave front, flat wave front. And when that goes through a conductive material, like the continuous wave other continuous wave electromagnetic methods, induces secondary fields. So we can measure these secondary fields to locate the conductive materials. Again, why we pick VLF for drone application? Because we don't need a source, and creating an electromagnetic source requires a lot of power, so a lot of additional batteries and weight. Here we just are using a receiver. And because this is an electromagnetic system, it is going to get affected by the electromagnetic noise created by the drone. So you have to hang it down on a tethering rope. This is like 10 meters distance. When you are flying over or collecting data over something, say like a fault or a dike, some really strong, big target, the data collection is quite, straightforward and easy, and your anomaly is going to be pretty significant. But when it comes to the drone-based application and you hang your probe down at the end of a 10-meter tether rope, then you have to deal with roll, pitch, and yaw, because the VLFEM is a highly geometry dependent method. Your probe's orientation compared to the incoming field is important for data quality. This is actually on the left side is a model created using COMSOL multiphysics in computer environment. So what we did with my PhD student, this is an ongoing research. We applied the yaw and pitch changes of one of our regular flight experiences to our model. It's a fault, right? And over here, the black line is the in-phase component of the electromagnetic measurements. And you still see that it looks like what I showed you a minute ago in the previous slide. I still can locate the fault because this is a strong target. And with this changing pitch between plus minus 5 degrees, nose up, nose down, and changing yaw around plus minus 10 degrees towards east and west, I still can see the data. And on top of that, I can obviously correct my data. This is the main goal of our study here. This red line over here is the data we corrected using some numerical methods. Then this black line affected by the yaw and pitch. So it is great. When I have a strong target, I can detect it. Even if I don't apply these corrections, I still can see it. But what happens when you have a small target? So here on this aerial photo, you see this white area that shows our flight domain. And this little yellow line in here shows an electrical resistivity profile, which is over here. It's like 250 meters long profile, goes down to 10 meters depth. It's a dipole-dipole array. And you see these three little conductive anomalies. These are pipes, galvanized steel pipes buried underground around 3-4 meter deep. And this is our test site. We fly over these pipes to hone our craft, basically, with the drone-based VLF electromagnetic. So on the left side over here, what we see is the same way computer model run in COMSOL multiphysics by utilizing these pitch, roll, and yaw values changing. And these are again taken from a real flight. So we just induced them to our computer model and ended up with this black line as our in-phase component, right? And in an optimal situation, those two pipes should show up with this little staggered anomaly. These two are too close to each other to be resolved separately. So these two anomalies are kind of superimposed, but we see them. And when we apply the effects of pitch, roll, and yaw in our model, now the data is completely undistinguishable. Like you can't say anything about it right now. What we do, we use our correction process, numerical correction process, to correct our data from this black line to the red one. And you can see that this red corrected line is pretty close to what we had at the end of our optimal modeling effort. So this is one way of correcting our data when it comes to small targets. This is another thing we did. This actually is a new way of, a new style of flight planning we came up with my PhD student. On the left side, this is a regular racetrack style flight. And you see on a rose diagram the yaw, pitch, and roll values of this flight. And you see how the yaw values are much spread it, and we even cut some of the extremes. And here are the pitch and roll. Pitch and roll are much more limited because wind helps with the wings of the probe. This new measurement setup we came up with actually eliminates the stray yaw readings a lot. So see on these right and left sides, we lost a whole bunch of stray points, and our yaw values are more focused on towards north and towards south. This is what we were trying to achieve. And in terms of our pitch and roll values, we don't have much change. But if you compare these are the in-phase components actually plotted with the same color scale, the left one to the right one, you see over here we have our three anomalies really clearly visible for our pipelines. And I also would like to show a video of our instrument in Utqiagvik, open tundra. This is a work in progress right now. We are still working on our data and getting ready to publish. And this other video is actually coming from the same location. This time we are measuring ground penetrating radar on a drone platform. Again, this is an ongoing work. So yeah, this is it. This is what I'm gonna tell, what I have to tell. Is there any questions?
Thank you, Minnie. You packed a
Thank
lot of
you.
information in our 45 minutes presentation. Uh, well, fortunately, your talk is recorded, and then I'll upload your webinar on the USP website, so our
Mm-hmm.
members can continue to watch, and I'll share your slides with our participants. Um,
Okay,
yeah,
that's
thank you,
great. Thank
Minnie.
you. Thanks very
Um,
much.
we have 10 minutes. I wonder if you have any questions. We have one question, and feel free to type your question, if any, under the
I
Q&A
see one.
section. Yes, go ahead. And can you please first read out and then
Yes,
answer the question?
so it is a question that says, does the speed of drone shows any variation in the data? Yes, it does in two ways. One, when you are flying faster, you are still limited with your probe's sampling rate. And when you're flying with 3 meters per second, you are measuring data for every 30 seconds, sorry, it's 30 centimeters with 10 hertz sampling. When you are flying with 10 meters per second, then you are measuring data for every meter. So flying faster reduces your spatial resolution. On top of that, because there are a lot of dynamic forces involved, especially with this VLF setup, if you fly too fast, the strain you put on the drone to maintain the weight as an active force is much harder to maintain for the drone. And on top of that, the swaying motion of the probe is not gonna go down very quickly. So you are going to lose much more data to this changing 3D geometry of the probe. So we have to find that sweet spot for both spatial resolution and also keep our probe in line, like in a tamed manner.
Thank you, Minnie. Well, I understand today, you couldn't, some your camera is not working, so you couldn't.
No, no,
Yeah.
it is an unfortunate thing, but yeah.
Uh, okay, so another question.
Oh, okay. So another one asks, Thank you for, I hope it was helpful. Could you please tell us what is your low frequency range? What is the corresponding survey resolution? Okay, so with the low frequency range, we are using the military radio stations and their frequency range is 15 to 30 kilohertz. Depending on the electrical resistivity of the ground material, we can go down to several tens to 100 meters or so with that frequency, like generic skin depth equation we use. So the depth resolution, non-existent, because again, the depth information is qualitative with these electromagnetic methods, but we can put this information, this data through inversion to approximate and get some quantitative depth information. And we did that, but it is not out yet in terms of our paper. The survey resolution also is related to the spatial resolution. And for our work, I believe we had few meters cross line and a meter inline separation when we were collecting our data in open tundra. Another question, two questions. Do you need any calibration for your setup? No. You do not have any control over the source with VLF. You need to be careful about the initialization process, about how fast you are. Like the instrument allows you for a faster sampling, for example, but when you do that, you are not giving the electronics time to line up with what's going on. So it actually, if you sample with too high sampling frequency, you lose data quality. So you need to find that sweet spot. So that can be a calibration thing. Also, we scan for which military radio stations we are actually receiving with a good power. That is one other thing we do. Also, the directionality of the military station is important. It should be lining up with our target's prospective direction, possible direction. So this is another thing. Again, the frequency range is 15 to 30 kilohertz. If you're asking about GPR, we used 500 megahertz antenna for our airborne GPR work. Another question. Oh, can we correlate the data with actual ground data and what is level of confidence of the data with actual ground condition? Yes, this is great. Yes, we have an on-ground conventional VLF electromagnetic instrument too. So while we were out there collecting airborne data, we also collected on-ground VLF electromagnetic data, and we collected on-ground EM31 electromagnetic induction data and ground penetrating radar data. Yes, as geophysicists, that is our common way of doing the work. We just go for more than one method, and we had quite a bit in this case, and it actually is a really nice agreement we are seeing. You also can think about that pipelines I showed in our test site, electrical resistivity data coupled with VLF. It shows that the data is legit. Another question, for methods that measure resistivity, are there established norms for deciding what resistivities correspond to active layer and what resistivities correspond to permafrost? I have seen a wide variety in the literature with values between 3,000 to 10,000 ohm meters, and I'm looking to understand if more firm recommendations exist. Yes, there are ways to know, but the problem here is not us not knowing the electrical resistivity values. It is the ground, the earth itself being too heterogeneous. So the active layer, its composition, its heterogeneity, its distribution, its content is different from 1 meter to the other one. So in that case, we can, yes, have some ground samples to ground truth our data. But when we are doing that, we also need to keep in mind that the ground itself is heterogeneous. So believe me, you can find an individual ice wedge with 3,000 ohm meter electrical resistivity and another individual ice wedge with 10,000 ohm meter electrical resistivity, depending on its density, how homogeneous the structure is, how big the contrast compared to background is. So these ranges are also about the heterogeneity of the ground. I hope this helps. Uh, I have two questions for your drone GPR survey. Which GPR did you use? Have you seen any drone geophysics applications for the coastal environment with seawater? I use sensors and software. Uh, Pulse Echo Pro. It's a shielded system I use. And I use a SPIDAR for Wi-Fi connection to the antenna so I can simultaneously see the data collected. I did some tests in terms of the saltwater intrusion, and our preliminary work kind of got wasted because we couldn't get the funding for the project proposal we submitted, but I am open to try it in another place. And again, it is about the limitations of the GPR penetration. If the seawater is in top maybe couple meters, we can see that. But if not, I suggest you go for a frequency domain electromagnetic method instead of GPR to use on a drone. Another question, have you been able to compare these UAS and ground-based geophysical methods? Yes, I think I answered that already. Okay, so yeah, these are all the questions.
Thank you, Minnie.
Thank you.
Any other questions before we finish? Well, I have a question, and probably for our audience in terms of adopting this innovative methods and technology of a drone-based geophysical imaging.
Mhm.
About the cost. I know
Ooh.
it really depends on I know it depends on the instruments and the drone and what you really want to measure. But what can you give just one example of a cost?
Okay, this is not an official example, but this is what I tell my PhD students flying the drone with the probe.
Okay.
First, I'm going to tell about our process. Before I allow a student to fly the actual probe with the actual drone you've seen in this presentation, I first have them fly $100 training drones and then have them fly a DJI, a couple $1,000 worth of a drone. And then they switch to the original drone, Alta X. And when they're flying Alta X, they don't use the probe itself. Instead, we have a dummy with the same geometry and same weight of the probe. So they fly the dummy. And once they pass all these, they start flying the probe. So this basically, I think, tells how expensive it is. And every once in a while, I throw in, hey, you are flying $200,000. Be careful. Just give them a little bit of, stress. No, it's not that expensive, but I think to start a similar setup with ours, you need 120K or so to drop.
Okay.
Yeah,
Got it.
it is
Thank you.
expensive. It is
Yep.
expensive.
Yes. Got it. Okay. Well, that
Maybe I
concludes.
can add this. Sorry,
Hmm,
sorry.
Go ahead.
Also drones, while they are in the air, they aren't insured. So if you have an accident during a flight, it is going to be very hard to get the system back up and running. It takes time and it takes a lot of extra to pay. Like your student can drop it off of the van while you are unloading it in the field, and it's okay. Insurance is going to pay for that. If you damage any third-party property, insurance is going to pay for that. But they don't pay for the drone itself. So
Mm.
this is one other thing that I like to complain about every once in a while.
All right. Thank you, Dr. Minnie Doan, and appreciate your talk very much. And this concludes our webinar. And thank you all.
Thank you. Thanks very much.